coming to liquid fuels, so liquid fuels were most prevalent till about 10 years back when they became expensive. All along, crude oil became expensive, and then people started really looking at their input costs. And there was a lot of switch which happened from liquid fuel to the solid fuel fired boilers. But still, liquid fuel still comprises a significant proportion of the fuel which is burnt in process boilers or furnaces, not for the water heaters. Because I mean, if you compare between just to give an idea about the two, oil-fired boilers are still, they occupy a small space compared to the solid fuel-fired boilers. I mean, solid fuel-fired boilers, I think if you ask me, it is like operating a plant within a plant itself. As compared to that, an oil-fired boiler is treated as a separate unit equipment, and then left it is. So not much importance. In the case of liquid fuels, very important that we get the atomization correctly. Because again, as I said, the principle of combustion doesn't change between solid and gas. So you need you need to get back to the combustion triangle. Yeah. So you have fuel, you have air, and the activation energy. Okay. So even in the case of liquid, so you have a liquid droplet. Just imagine a liquid droplet. Even the liquid droplet will burn in the surface only. And as the liquid droplet burns on the surface, newer surface will get exposed, which will also burn. Right. So the idea is basically to atomize the liquid droplet and get the best atomization which is actually possible, so that your example very quickly burn volume of liquid that you have. All that happens inside the burning. You may use various technologies. I mean, you may have a mechanical way of atomizing, or you may have a pressure jet atomization, or you may have air atomized burners, or for that matter, steam atomized. But the idea is to atomize so that you expose maximum surface of the liquid. And rest of the process follows the same thing. You are able to control the air and the liquid fuel. And here, again, the challenge is you want the burning to take place within the chamber itself. Within the furnaces. Yeah. Anything which goes beyond the flame is an unbound speck in your
Understood. When we talk about atomization, what would be the rate? So atomization is basically just creating droplets, basically minute from. What is a typical diameter, which is, like you would say that this is kind of a good or optimum size for an atomized droplet?
I will tell you what we get. So normally in pressure jet burners, we get a band of anywhere between 80 to about 120 microns. Okay. That is the
diameter of the drop.
Diameter. Whereas in the case of rotary cup burner, it is much more condensed. I mean, so we have a distribution which is much more on the lower side.
Yeah.
So we get anywhere between, let's say, 40 to 80. So, so much finer, much better. But then again, the challenge is you have one more rotating part. There is more might at least. So that way, it becomes disincentive for us to get on to mechanical atomization. But we are able to get similar results with steam jet atomization is their atomization. And with those kind of particle droplet size, we are really able to get good results with respect to the onwards. In fact, you hardly have, if you look at modern day burners, the combustion efficiency is as high as 99.9%. There's hardly anything which is left uncombusted as a result of atomization per se.
Right.
We may get into a problem of air to fuel ratio is something else. It is a part of the normal troubleshooting manual, but not this.
Yeah. From the principal perspective, both from a fundamental understanding of the concept to the actual implementation of it in an industrial system, most of that has been actually worked on pretty well, and the results we have in the industrial system are one of the peaks, I would say, in that game.
That's the thing.
Yeah.